All right, guys, so talk about your two experiments that you'll be doing today. The first one is free fall. The objective of this experiment is we're just going to drop a marble from varying heights and measure the amount of time it takes to fall those heights. We're then going to graph the height versus the time squared value, and in doing so, we're going to calculate the slope of that graph, and I'm going to be able to tell you what it represents, what it should be for a value. So, I think if I'm not mistaken, most of you should have a marble at your table, but if you don't, I've got them floating up front. I'll be able to give everyone at least a marble. All right, so you have a black box on your table. What you want to do is hit the red button and scroll through to time. Then you'll hit the blue button and you'll scroll through to stopwatch. And then the black button signifies that you are ready to go. So what you want to do is, I'm going to clamp the marble in position at a given height that I've measured. So I gave you 4 different heights that you're going to measure, 0.2, 0.4, 0.65, and 1.2 meters. Measure out that height, measure from the top of the pad to the bottom of the marble, because that's the total distance that it falls. Then you want to go ahead and once you've clamped it in position, now you're supposed to clamp it down. You don't need to do that. What I do is I just put the marble in and I press down on the clamp and hold it there with my finger. And then what I do is I hit the black key to start, release, it drops. Once it releases from this copper piece, it activates the timer to start. Once it hits the pad, it activates the timer to stop. So that's how it measures the amount of time that it takes to fall over that distance. So in this particular case, whatever that height is 0.2152 seconds. If you get any values that are like 0.0001 or some really weird value, it's an outlier, okay? It's basically this contraption's double triggering and got to get it to stop. So if that happens repeatedly, if it happens, try it again. If it happens repeatedly, call me over and I'll try to work out the kinks. But once you have that time, you'll write it down in the T1 spot for the given height, T2, T3. So you continue to run trials over and over again. And it's real simple. 0.21. So you'll do that for 5 trials at each of the given heights. Then you'll take the average time by taking all these heights and adding them up and dividing by 5. You'll get the average time, and then I want you to square that value, and you'll have a column for the average time squared. Okay? Now, something that I want to mention. This formula that I've given you here is the kinematic. Now, I'm not sure. Have you guys talked about the kinematic equation yet? It's always funny because I always get like half the head and half of them no, and it's like, of course, anyway. All right, so the kinematic equation, in case you haven't seen it, looks something like this. Total distance is equal to x naught plus v0t plus 1/2 at squared. Does this look familiar to anybody? Yes, no? Yeah, so that's half head nods again. All right, so in this particular case, we're just measuring the total distance. There's no initial velocity, and the initial displacement, if you will, would be this. The total displacement x. So subtracting this to this side, you get x minus x naught, which is the total distance, and that's equal to 1/2 at squared. And from that, the acceleration in the system is g, the value of gravity. The value of gravity is 9.81 meters per second squared. It's relatively constant around the radius of the Earth. All right, and h is the difference between its initial position and its final position, which is just the height it fell, right? So that's where this equation comes from. The point I want to make is, at any point in time, when you get your data points, if you square the time and you plug in the value for the height and you solve for g, you should find out that it comes out close to 9.81. All right, and that's just one of the little tricks I want to teach you so you can double check your values and make sure you're where you need to be. Okay? All right, so once you have all your table filled up with your heights and your time squared, you're going to graph them. You want to put your height on the y-axis and your time squared on the x-axis, and I'll give you a little bit of a spoiler, but you should find a linear effect. All right? When you turn in your lab report, you will do a graph in Excel, and you'll do a line of best fit based off of that slope for these scatter points. Okay? Now, what is a slope? What you'll do in class is I want you to take at least 2 successive points, and I want you to find the slope between them by finding dy dx. So change in y over change in x. And I want you to come up with some sort of value to tell me, all right? And then I want you to tell me what the slope should be. And the first week, or I'm not going to give it away this week. Basically, I'm going to go around the room and explain to you how to determine what the slope should be. I'm going to teach you a method on how to determine what the slope should be, which you're going to use again in 3 weeks. So in 3 weeks, we'll be doing a pendulum lab. And in that same lab, I'll do the same treatment where I'll say, graph these two values. What is the slope and what does it represent? All right? So whatever the slope you find experimentally based on your data, and then I will tell you the theoretical one when I'm going around the room. Once I tell you how to calculate the theoretical one, those two values are the values that you'll compare for your percent error for your report. Okay? And that's all there is for that lab. All right? So I'll go over into this lab. This lab, Newton's second law, is basically we're going to race a cart along a track and get it to accelerate with a driving force of a hanger and masses. So the first step in the procedure is to find the mass of the cart and the hanger. So taking all the weights off, this is the cart, this is the hanger. Put it on a triple beam balance and you can calculate what the mass, or you can measure what the mass is. All right, just be careful because I think there's a problem with one of those triple beam balances as of yesterday. So just be careful and make sure you're getting the right value. The cart should have a mass of around 520, all right, give or take. So if it's way off from that, call me over, let me take a look. The first step after that is to then place 30 grams on the cart and 10 grams on the hanger. So put 30 here, I'll put 10 on the hanger. You'll suspend the hanger over the side. And the next step is going to be the most important step in making sure that you have good values. Okay, so it's very important that you pay attention to this step. All right, your box will say time, 2 gates. All right, most of them are probably already set up that way. I'll hit the black key to start and get it ready. And then I will move the cart to where the black strip goes through the sensor. Now these gates have little pinholes in them, and the pinholes could be raised higher. And that's what happens if you race the cart along and nobody catches it. It falls on the floor. That's that sound you just heard. I know that sound. So yeah, you need a cart catcher for this lab and make sure that nobody breaks stuff. So once it's started, these little pinholes have a laser going through them. And they sense when one of these black strips interferes with a laser, kind of like a convenience store when you walk in and it goes bing bong, right? All right, so I'm gonna move it into the sensor and the light on the top will activate telling me I'm in the sensor. I'm gonna move it just back left of that so I know that I'm immediately to the left of it, and I'm gonna double hit the black key to start it over, then I'll release. It'll accelerate through the gate and it'll measure the amount of time it took to go this distance with an acceleration. Now the reason I'm doing this, and I'm very strict on that method, is because the equation that I give you for A experimental is 2d over t squared. That is a rederivation of the kinematic equation above, all right, with the grounds that the initial velocity is 0. So if you need to start this as close as you possibly can to the gates. If you start it too early, it's going to have a velocity when it starts going through the gates, all right, which means that that equation isn't technically right, and neither is your calculation. All right, so that's why I'm showing you that method. So you'll measure the amount of time that it takes to go through the gates, and I'll give you a little bit of a hint. The first time for the first mass and setup should be right around 1 second, almost on the dot. So then you'll calculate the experimental acceleration by taking 2d over t squared. D is the distance it travels. In all of your cases for your setup, you have your gates are separated by ½ a meter, okay? So 2d is just 1 meter. So it's just 1. You don't have to put anything in. You just put your t squared here on the bottom and you calculate the acceleration. When you make these measurements, take at least 3 trials to be sure that you get a repeatable time. All right, remember everything you do has to be repeatable. I think if you look at the online version, it says take 5 trials. I'm only making you do 3. Just make sure that you can repeat the same number over and over again. Then you calculate the experimental acceleration and you'll compare it to the theoretical. So in the theoretical case, we have a driving force, which is whatever the cart is times gravity, all right, and that's what's pulling the system. The system in motion is the mass of the cart and the mass of the hanger, and it's going to move with some acceleration. Now, it's not accelerating at gravity. If it did, it would be a free fall acceleration, but it's obviously going slower than that. All right, so little m plus big M is the system which moves with some acceleration A. All right, big M, now this is the important part. Big M is whatever the mass is of the cart and whatever's on it in each case. All right, so in the first setup, you have 30 grams on the cart and you have the mass of the cart. So if the cart has a mass of 520, big M is 550, right? Little m is the mass of the hanger plus whatever's on the hanger. So in the first case, if there's 10 grams on the hanger, then it's 50 grams for the mass of the hanger plus 10, which is 60. Okay? So I'll give you a little example. A theoretical 1 would look something like 60 divided by 500 and, let's say, there's 30 on the cart, it's 520, so we'll say 550 plus 60 times 9.8. Okay? So that's what you plug in the first case. This equation that I've set up, just to show you, moving the acceleration, dividing this to this side is what yields that equation. Little m over big M plus little m times gravity. So that's where the theoretical one comes from. Once you've calculated the theoretical value and you've compared it to your experimental value, you'll do a percent error, all right? And then you'll go on to the next step. The next step is to take 10 grams off the cart, move it to the hanger, and then repeat the whole process all over again. You should find as you put more mass on the hanger that it accelerates faster, all right? But this value will go up, so will this value because you'll be changing these M's and big M values, okay? All right, so you'll do that, repeat it, percent error, then you move 10 grams again, and you'll do that 4 times until there's no mass on the cart and all 40 grams are on the hanger, all right? And then you'll be done, okay? So does that make sense for everybody? All right, so your percent error will be, you'll have 4% errors effectively. You guys only have 1% error based off the slopes and what it represents. Are there any questions before we start? Okay, so I'm gonna be going around the room, just get started. I'll be able to help you out and we'll iron things out as we go.